Okay, thank you very much. I would like to start with thanking very much the organizers, but also the directors of the institute, both the present and the previous director, for the opportunity to come here and spend the 3 months of my postdoc, which is this EPDI here. So I've been in Paris, in Zurich, and now here, but I'm going back to Zurich. But this is mainly work I did in Stockholm, but also in Copenhagen, where I was 1 year for postdoc. So that explains my affiliation. So I would like to start with a very brief introduction to the supermembrane matrix models from the membrane perspective, just to set notation and context. And then we will discuss the main issue, which is the spectrum and ground state conjecture. And also I would like to just want to point out that I'm approaching this problem from a mathematical side. So in case you have very technical physical questions, I might not be able to answer that. And then we discussed the recent proposed approaches to study this problem and an outlook. So the supermembrane matrix models, just to put some notation in very briefly, is this is the partition function for in the bosonic case. So it has to do with a tuple D traceless Hermitian matrices, n by n matrices, and the potential, which makes it very complicated to study this from a mathematical point of view, is of this form, is a trace of a commutator squared. So really the problem is when this commutator vanishes, when the matrices commute, you have flat directions in the potential and you have problems. And these models arise from various contexts in relatively recent physics. One, which is the point of view I would like to look a little bit in the introduction here, is the extremal supermembranes in 1, d plus 1 dimensions. So it has to do with a light front approach to this. So d will be the main parameter here, together with the n. But also as a reduced dimensional reduced theory of super Young-Mills theory in 1, d dimensions, so one space-time dimension lower. But also this model arises when you study from string theory. You study models of big N d0 branes, and the question of zero energy states is then question of bound states of these d0 branes, and also through the so-called BFSS conjecture, this has been relevant for M theory. So a very old, perhaps from a physical perspective, review of these models is by Taylor in 2001, and this might be outdated by now. And from the mathematical perspective, this a little bit more recent review is in my thesis from 2010.
Can I ask a
Yeah.
question? Is there any time derivative?
No, so this is not involved. This is just so this is not the full action, but this is just concerning the potential. We will come to the full models shortly. This is just to.
You're doing quantum mechanics, though. You're not just.
It's quantum mechanics of these matrix models, exactly. So let's. I just mentioned. So the question of zero energy states would be in this context is a question of the zero energy concerns the internal energy of the membrane in that case. So there's sort of bound states or stable states of the membrane with zero internal energy. The Young-Mills theory concerns you can think of bound gluons essentially, or some gluon composites, or some people call them glue balls, and then you have the bound states in the string and M theory perspective. So let's just delve into some context from the membrane point of view. Start out with the bosonic case, which is simpler. So we start out with some world volume topology. So you take some fixed compact two-dimensional manifold describing the membrane, and you think of this manifold evolving in space-time. So you have some sigma here, but then you think of this as evolving in space-time. So you have the R times sigma topology, and then you embed this into some underlying flat space-time and in light front coordinates. So that's why it's only the RD remaining here. So you have taken away the R1, 1. So these are the xj are the embedding functions into this transversal space-time. And a resulting Hamiltonian for this is, so now we have the kinetic energy of this embedding of this membrane, but also coming from the metric of the embedding, there's a term here involving the derivatives of the embedding functions, so the spatial or on the manifold sigma. So this is complexly written in terms of a canonical Poisson bracket on sigma. Since we have two-dimensional manifold, it's a canonical Poisson bracket just involving the antisymmetric derivatives of the functions, and you square that and you sum over all the different coordinate.
So what's the light front story? Where did two of your dimensions go?
So you starting out with, essentially you have, it's R1, 1 plus D, but then you consider the 1, 1 to be, or the light cone in the 1, 1 directions. So you have some coordinates there, but then when you want to consider the internal energy of the membrane, these drop out from the story. So actually this is not the Hamiltonian in the traditional sense, but this is essentially describing the internal energy of the membrane. And then in this light front approach, these coordinates drop out, and it's only the transversal. So at each point here we have the transversal RD dimension, and it's only those coordinate functions that come into the internal energy. So this is
it's like light cone quantization for the string.
Yeah, this is a like
your R is sigma minus, say, and sigma plus is just dropped. Everything's independent of sigma plus. Is that the?
Yes, in the internal energy. So when you have taken away, so there's a way to rewrite the Hamiltonian, or you can perform a Hamiltonian reduction from the original space of coordinates down to this internal space. So yeah, so just briefly, I don't want to go into details of that because this is reviewed earlier in this.
Then it's surprising that you don't have constraints anymore.
Okay, yeah, so you have constraints, and that's so there are constraints from the diffeomorphism invariance that you have in this series. So you have also residual diffeomorphism invariance, which I will come to also in the matrix regularized picture. So so essentially you start out with the full theory and you have certain constraints, but then you can solve some of these constraints and you reduce down to this simpler. There's a little bit more recent paper on more of the details on this Hamiltonian reduction. I can give you references later, but so you solve some of the constraints and then you end up with a simple theory, but you have more constraints, and it's essentially the remaining diffeomorphism invariance, where you have volume preserving diffeomorphisms on that manifold sigma. So if we go over to the matrix regularized picture, so this is also old work, but the idea is to replace this infinite dimensional algebra of functions on sigma. So these coordinate functions are part of this infinite dimensional algebra, but you want to approximate this algebra by a finite dimensional. So you go from this infinite dimensional Poisson algebra of zero average real valued functions to n squared minus 1 dimensional algebra of traceless Hermitian n by n matrices xj. So we replace the coordinate functions by coordinate matrices xj, where the Poisson bracket on the surface goes over to a commutator of matrices, and the integral is replaced by trace, and the approximation or regularization is in the sense of convergence of structure constants in this algebra. If you choose your bases on this side correctly, you can make them pointwise converge to the other bases. So or to the other structure constants. So what I wanted to come to is this symmetry. So on this side you have this diffeomorphism invariance you act on these coordinate functions, and that the nice thing about this regularization approach is really that you can capture these symmetries also on the regularized side. They become or are manifested by SUN invariance instead. So in the end, if you work out the technicalities, the resulting Hamiltonian is now involving the kinetic energy, so that's just derivatives of these matrices, and then that term I had before involving the Poisson bracket goes over to the matrix commutator. And the really nice thing is that you're now in a finite dimensional setting, so you have finitely many degrees of freedom. So this you can quantize by standard methods, the Schrödinger and the Dirac quantizations.
I have missed one thing. Why was it zero average?
Okay, so yeah, maybe I should have clarified a little bit. So this is again the internal energy is only on the so you integrate out the center of mass of all the coordinates. So that's separated out into a center of mass, kinetic energy, and so on. And so this is only, so the internal energy only involves, so this is already derivatives on these functions. So the constant part is dropping out, and these xj's should be the center of mass versions of these coordinates. So that's in the internal. So because you have a integral zero of those xj's, you should go to traceless matrices. Okay, so we quantize this in a straightforward manner, replacing the xj's by coordinate multiplication operators and the p's momenta by differentiation operators in the standard Schrödinger representation. The Hamiltonian then goes over to, so the p, the kinetic energy part becomes then just Laplacian on the space on the configuration space that we're dealing with. While this written out now, this potential term, this commutator, in terms of the structure constants f, a, b, c of SUN. So this becomes just a quartic polynomial in the xj's with certain features which are important we come to. And importantly also is this physical Hilbert space. So you demand your, you started out with a diffeomorphism invariance, so your physical states should be diffeomorphism invariant, and this goes over in the regularization to that the physical states should be SUN invariant. So you have these constraints which are now on the quantum level. So that's why it's Schrödinger Dirac quantization, because you have these constraints. So a physical wave function psi should be annihilated by all these constraints where you have the freedom of a going from 1 to n squared minus 1. So this regularization approach in quantization was originally considered by Goldstone and Hoppe in the early 80s. And you can also extend this to a supersymmetric version. Of course, adds a lot of technicalities, but so if we want to add spin degrees of freedom, because we want to consider supermembrane or the super Yang-Mills theories, you arrive at the supersymmetric quantum mechanics in the end with the finite degrees of freedom. And so this involves the Clifford algebras. So you started out with a RD space, and in this RD you have corresponding gamma matrices, Clifford algebra with a real representation R to some ND, which I will come to. And over the corresponding space, Rnd and Rn squared minus 1, you have also you can also form a Clifford algebra, or you can think of this as being the fundamental fermionic degrees of freedom, fermionic creation annihilation operators of the theory, acting on some irreducible Fock space F of this nasty dimension. so this dimension grows very fast, and that makes it very difficult to study this when you in the highest dimensional context. And the corresponding Hamiltonian is just the original bosonic part of the Hamiltonian, but then we add to it this fermionic part. And the things you have to notice is that this is just linear in coordinates. The rest here is essentially just a matrix involving this creation or these Clifford variables, these fermionic variables, and you have just the structure constants of SUN, and you have the gamma matrix elements of these gamma matrices. So this is now, well, I will come to this in the quantum setting, but essentially this is just then a Schrödinger operator with a matrix terms. You can think of it as a matrix Schrödinger operator. And it has supersymmetries, so there are certain supercharges, ND of those corresponding to this irrep of this form, but the key is that they form the supersymmetric algebra so that the anti-commutator of these guys become proportional to the Hamiltonian, but you have an additional term here involving the generators of the SUN symmetry or invariance. So when you look at the physical Hilbert space where this should be 0, then you have just the supersymmetric quantum mechanics. And a requirement, importantly, in this supersymmetric context is, in order for this to work out, in order to have supersymmetry like this, essentially this relation to hold, you have to have the dimension to be either 2, 3, 5, or 9. So this is the classical requirements coming from certain fields identities. So this is even on the classical side, it's not quantum mechanical. And corresponding to these dimensions, you then have the number of supercharges, 2, 4, 8, or 16. So typically one is mostly interested in the 9 case with 16 supercharges. So the full Hilbert space in the end is just the original bosonic Hilbert space. That's just square integrable functions on this bosonic configuration space. But now we have also this fermionic Fock space F. And as I said, the physical states should be annihilated by the generators of the SUN symmetry, and that's as in the bosonic case, but extended with some fermionic part. And there was actually a SOD symmetry in the original bosonic model also. You can rotate essentially among these in this D tuple of matrices, but that goes over now into a spin D symmetry, where the SOD is now extended with this fermionic part, so that you get a spin D symmetry. And in the context of the Yang-Mills theories, this was considered in the around 85 by Bakker, Reinecke, Rittenberg, Clausen, Halpern, Flume. And in the membrane context, it was considered by De Witt, Hoppe, Nicolai in 88. Okay, so now let's go into the mathematical problems of this, or why is it tricky to study this. So if you consider the potential of the model, so on the classical side, this is just well, a sum of traces of squares of commutators essentially, but one thing to notice is that this is actually non-negative potential everywhere in the configuration space, but it has the complication that if the matrices commute, then this is 0. So you have certain flat directions of this potential. And in order to understand the difficulties, it's very useful to keep in mind a certain toy model in the plane. So I just sketch what we mean by this. So we have essentially just the x and y directions. And we consider a potential x squared, y squared. So if you draw some equipotential curves here, it looks something like this. And of course, it goes rapidly to infinity in these directions. But along x and y equals 0, along the axis, the potential is 0. It's flat. So from a classical point of view, if you would have a particle in this potential, you could start out on a potential value like this on the axis and just escape to infinity. So from a classical point of view, this would be an unconfined potential. But on the quantum mechanical side, you get a certain energy because of these values are actually becoming steeper and steeper on the sides here when you go further out into and because of that, it's not a confined potential anymore, essentially. So, so if you consider the bosonic operator again, on the quantum side, this is a Schrödinger operator with this potential. And again, you can consider a toy model for this. So it's just, well, the Laplacian in the plane plus this x squared y squared potential. But if you make a certain smart trick and rewrite this operator, so you take out essentially just the half of the kinetic energy, and you put half here, you put half here, and you split this into two. Then you can see that this actually involves a harmonic oscillator in the x coordinate with frequency y here, and here is a harmonic oscillator with frequency x. So using that the harmonic oscillator has a lowest energy state being equal to the frequency in this case, you can bound this from below by modulus of y and modulus of x. So you have a bound of this operator from below by this operator, which actually has potentials going to infinity everywhere. So this has a confining potential. So that's because of this lower bound by an operator with confining potential, you actually have a confining. It will be confining also on this side, and more exactly, this is a purely discrete spectrum bounded from away from zero. This operator. So, and this was considered in the matrix model case or Young-Mills theory case by Lüscher in '83, and also that the full model, but also this toy model was considered by Barry Simon in '83, and he gave actually several proofs for the discreteness of the spectrum, essentially 5 different ones. So this is interesting from a mathematical point of view, spectral theory. But recently this has also been extended by Garcia del Moral and collaborators to other potentials, so essentially potentials with certain similarities but more complications. So these potentials are relevant for the BLG and ABGM type theories. So essentially you can prove discreteness of spectrum for bosonic operators also in that case. So let's now look at the supersymmetric quantum mechanical model. So even though we thought everything was fine on the quantum side, for the bosonic case, things again become complicated in the supersymmetric quantum mechanical case. So we had this bosonic operator times a unit matrix you can think of, but then you have this matrix part added to the Hamiltonian. So even though it's just linear in the coordinates, it has certain features which makes it complicated. So let's first look at, you have the Hamiltonian on the physical Hilbert space. This was just a square due to the supersymmetric relations. This is a square of a bunch of supercharge operators. So because it's a square of some self-adjoint operators, it's non-negative on this space. So at least that's nice. But if you say, you can also look at a toy model for this case. So it's again useful to come back to the toy model, but then we extend this bosonic toy model with a certain extra part here involving the usual Pauli matrices. So this is also linear in the coordinates involving some 2x2 complex matrices, but and you can also write that as a square of some other operator. So it's also non-negative, but the problem is that you have a certain cancellation in these valleys. So say that you look at well, you have essentially so let's see, we can look at a part of the operator in this valley. So so let's go along the x direction, and you have kinetic energy in the y direction plus this bosonic potential, but well, involving the frequency now x. But when x becomes large, this is essentially, you can ignore y, then this is essentially just giving you a minus x. But this bound was just also involving X. So there's a cancellation in the bosonic and fermionic energies in this operator, and that is what makes it complicated. So actually, even though you had a purely discrete spectrum of the original one, this in the supersymmetric context, this model has not a discrete spectrum anymore. It has a spectrum covering the whole positive half axis. So if we cover the whole axis with this spectrum, and this was proven by David Nicolai in '89. And essentially, this means that the supermembrane is unstable. Somehow, you can the way you can think of this is that it can deform in certain ways without losing energy. And so this was thought of as an instability of the membrane, but it was actually crucial for the M-theoretic interpretation later. So, so essentially, the mathematical statement is that for any energy greater than or equal to 0, you can find a sequence of wave functions normalized such that the Hamiltonian minus this energy, the norm of that on the wave function tends to 0 as t. So you essentially find a so-called wild sequence for this operator, and this means that the spectrum of the Hamiltonian is actually 0 to infinity, considered always on the physical Hilbert space. So, and essentially for the toy model, the way to prove this is to take this is the ground state of the harmonic oscillator, so that essentially the ground state of this thing, and this psi means just the fermionic part giving you the negative energy here, and then you have some cutoff function to make this nice, but essentially it just amounts to taking a wave packet and sending it off into infinity and stretching it out and making it sort of nice and smooth. So, and this you can extend, but it's a little bit complicated because of the gauge invariance and so on.
So there is no energy gap.
Yeah, there's no energy gap between 0 and the spectrum. So that's why really this point here is interesting. The zero point here. So that's really the what we would like to study is whether this point 0 at the bottom of the spectrum, is that actually an eigenvalue or not? So that whether there is a stable bound eigenfunction at that point. So that's the question of ground states for this. And the so-called BFSS conjecture states that it depends a little bit on the dimension of the models. So for the highest dimensional case, which would be relevant in the M-theory context and the 11-dimensional supergravity, there should exist a normalizable zero energy ground state for all n. So because you would like to take n to infinity or very large, this should hold for every n. And also it should be unique such state. While for the lower dimensional models, the 2, 3, 5 case, there should be no normalizable zero energy state for any n. So even though these are not relevant for the M-theory interpretation, well, it's just that it's nicer if these are singled out, and actually there's a lot of evidence, as we will come to, telling us that this might actually be the case.
Why do people believe there's no ground state for the lowest supersymmetry cases?
Yeah, so, well, actually, I will come to this in the next slide, but one thing could be that you would like to single out the higher dimensional case to be relevant for
I understand whether
yeah,
there is
yeah.
one.
But we can look at it. I just want to mention, well, this was in the work of Banks, Fischer, Schenker, Susskind in '97. But I would also like to point out the fact that there is actually a degenerate model you can consider, like a D equals 1 model, where you can't have, so it's just one matrix, so you can't have a commutator, so the potential is 0, but you can actually formulate something there. And in this case, you do have a non-normalizable zero in your state, so it's essentially just a constant function. A constant function on the vacuum of the Fock space, essentially. So here you can answer this question, and you actually don't have a normalizable zero unit state, but you have a plane wave normalizable in some sense for any n. But usually you don't consider the d equals 1 case, but it also is connected to the, well, two space-time dimensional reduced Young-Mills theory. Okay, so now we come into this question. So why do you believe in this type of conjecture? Well, of course, this was later. There was a rigorous proof of this fact for the simplest case of the class of supermembrane matrix model, when you have d equals 2 and n equals 2. Then you can prove this by very technical arguments, essentially by proof by contradiction. So Fröhlich and Hoppe considered this. But also supporting this is, so this statement is, if you consider asymptotics, so essentially along the corresponding valleys, you can study the asymptotics of wave functions or eigenfunctions. And then you see that, well, if you go off the valleys, if you go into where the potential grows, then you have to have an exponential decay of the eigenfunction. But when you go along the valleys, since the potential is almost zero, you don't have exponential decay, but you have only polynomial decay. And this decay depends very much on the dimension. So, so for the lower dimensions, the decay is not sufficient, you find. But for the higher dimensions, the decay is sufficient. Of course, this doesn't prove the existence of a ground state, but it supports the conjecture. So this was considered by Halpern Schwarz in 1988, Fröhlich, Graf, Hassler, Hoppe, and Yao in 2000, and yeah, there are some other related papers also. And then, of course, from the physics community side, there's been very important Witten index calculations. And essentially, well, it seems like most physicists thought that, okay, this answers the question, but there are actually many open mathematical issues in this. But essentially, it was first considered by Yi and City and Stern, 97-98, and then this approach has been extended by Greengut, Perl, Kraut, Nikolai, Staudacher, Katz, Milgram, or Nekrasov, Shatashvili. And yeah, so there's been a lot of work on this, and the problem is really that this Hamiltonian is not, it has this spectrum. So, and because of this, you don't have a discrete spectrum, you don't have a gap, and all this makes it very tricky from a mathematical point of view to study this. So you have to have certain arguments for why you can apply this Witten index computation. And so essentially you have to evaluate a certain boundary term, and there are lots of complications, and then in the end you add up fractional indices into an integer index. But actually it was pointed out by one of the organizers, Bimbo and Muki, in 1984 already, that, well, there are problems when you want to evaluate the Witten index for problematic operators. And also in this Witten, in this context, it was studied by Staudacher in 2000. They found actually a contradiction to this method for at least for the exceptional or some exceptional gauge groups. So it's not clear that it actually is rigorous. And also Jaffe studied the problem in a similar context, the problem of studying invariance of indices from a rigorous mathematical point of view. Okay, so now let's come to the recent contributions to studying this problem from a rigorous mathematical point of view. So we have first of all a method concerning construction by recursive methods. So essentially you want to start out, well, you can start out from the asymptotics, but you can also start out at the origin and look at higher and higher orders and see what is the necessary structure of a ground state. And the symmetry and invariance and all that poses a lot of restrictions. So you can actually do something here. So it was studied by myself, Hoppe, and Chechilevsky, and then extended by Hinek, Chechilevsky, and Michishita. I will come to this shortly. And another approach is deformation. This has been considered before, but in the work with Hoppe and Czerszylewski, we consider certain octonionic deformation, which simplifies the operator, but the operator still has mainly the same problems, but because of simplicity, it might be easier to attack. Another approach is averaging with respect to symmetries. You had the spin 9 symmetries, and by considering a simpler operator, which arises as part of the original Hamiltonian and which you can understand fully, the idea is to try to average this operator and the states. And actually you can do something in this context. And another approach is by weighted spaces in index theory. So this is essentially allowing for more general eigenstates. So not square integrable ones, but so-called generalized eigenstates. So they are allowed to decay less rapidly along these potential values, and then you can actually form an index related to that, which I will come to shortly also. And this is by myself, and there are some mathematical technicalities that you need to deal with. I did it for the toy model, but in order to extend this to full models, you need to extend these tools, and this was a little bit discussed in certain papers on the archive. Okay, so let's consider the construction by recursive methods. And so as I said, you start out by the origin, you point x equals 0, and you expand the wave function just in higher powers of x. So this is then an element in the fermionic Fock space, and then you have higher and higher orders of this size in the Fock space. And if you just consider the zero any state condition that q, well, for all these alphas, psi equals 0, that puts certain relations between these Fock space elements. So here it's just a relation on the first order one. Then there's also a relation on the second order. But then as you go up, you have a relation between the third and the 0th, and so on. You can go on this. So the hope is that maybe if we understand the structure of the Fock space and how these operators act in the Fock space, maybe we can learn to higher and higher orders how the wave function should look. And actually, at least in the n equals 2 case, the amount of symmetry you have in the problem puts so much restrictions that actually this element here is unique, even though the Fock space is huge. It's 16 million dimensional or something like that. This is a unique state here which has all the symmetries that you need. So essentially the main thing here is that this requires, well, of course you have SUN invariance, that's to be a physical state, but also you have the spin D invariance for a zero NU state. So it means that the value of the wave function is up to a constant, has to be of a certain form. And this form, so if you consider representation theories, essentially in n equals 2 you have three copies of a smaller Fock space, which splits on the spin 9 into a 44, 84, and 128 representation. And by forming certain symmetric combinations of these, you can arrive at this, which has to have this form. So this is, I have this on the next slide. So essentially you just form a natural combination of the 44 states. So these are normalized in some natural way, and so you represent this by JK, and the 1, 2, 3 is the index in under the SU2 group. And
sorry, a really dumb question. Why have you got tensor products with 3 states? Where does
Yeah,
that
so
come from?
it's because of the adjoint representation of SU2. So we have n equals 2. So this is so you have well, essentially it's the indices. Let's see, the indices big A here. That's the SU2, the adjoint representation of SU2 index. So this is 1, 2, 3.
fact you want a singlet under the SU2?
Yeah, because you want it has to be SUN and spin D invariant. SU2 invariance is just SU2. It's just the gauge symmetry. Physical state has to be SU2 invariant, and the spin 9 in this case invariance is because it's a zero-any state. You know by a certain theorem that it has to be spin 9 invariant as well, or symmetric. Okay, so forming these combinations, so the 44, but then also you can form a symmetric combination of 44, 84, and 84. In this way, you have to have this certain combination of these two singlets appearing there. And this has been extended to at least one higher order by Michishita. So he found the form and proved the uniqueness of actually the next order of this. So we have the first two orders here. But the problem is that when you have n greater than 2, then this seems to become much more complicated, because then there's not a unique singlet here, but there are many, and so then it's not uniquely singled out, unfortunately.
So the size 0 is telling you where it sits in spinor space.
Yeah.
Essentially.
Yeah, so this is on the Fock space, the spinor space side of so this is the psi. So x are just the coordinates on the bosonic variables, but so at the point 0 you should have this element in the fermionic Fock space. So if you think of psi as a function on this Rd times Rn squared minus 1 to f, essentially.
And if you think about this as D0 branes, which is actually a super multiplet of D0 branes of particles of different spins, this is telling you the ground state consists of which combination of which particles with different spins.
Yeah, I don't know
translate
exactly
it
how to translate it into physics. It would be interesting to discuss that, because I don't know exactly what the physical interpretation is.
You don't worry about whether the state is normalizable or not?
Exactly, here we don't worry about that. This is just,
Important.
of course, this is important, yeah. So,
I don't
but
see how you can implement this, because you start with around the origin.
yeah.
So having just this.
Yeah, you start, but so, and again, it's proportional to this, so there's still some constant which is not determined by this.
I mean, you have a power series expansion. So how can you ever go to?
Okay, yeah. So at least so if you have okay, this is a good question. So if you have a state, if you have an eigenstate psi, so it could be a generalized eigenstate. So essentially. But since these Q's are also smooth, nice operators, you know that this function has also to be smooth. So if there is an eigenfunction, it has to be a smooth function around the origin.
But not analytic, right?
Even analytic, because these Q's are also analytic. Okay, yeah, we can discuss it, but I think that it's even analytic. But this also doesn't demand the analyticity. We could have put, okay, so maybe I wrote plus ... here, but maybe we can put the higher order element somewhere here.
What's an example of a nice smooth Hamiltonian where you don't have analytic wave function?
I think, but there are maybe some subtleties because of this SUN invariance and so on, so that I can't say definitely, but I believe it will be analytic. But in any case, if you consider the higher orders and you put the rest, the non-analytic part, into the remainder term, then this is perfectly fine.
You know there is a unique normalizable ground state. For this case, I think it was proven by Sethi and Stern.
Oh, so that's the Witten index.
I thought Sethi and Stern did a good. I thought they were the only ones that did a good job.
But there's still subtleties in this And also this is one part of the index. So the index is split into different parts.
It's that boundary term, but I thought, and that's what Kiljan did, but I thought Sethi and Stern did it, that was on Stern. Why Stern was on
But-
the paper, I thought.
It's a lot of work put into it, but
Still loopholes.
there's still loopholes. If you talk with mathematicians, they're not completely happy with this. So, okay.
I didn't quite understand why you can conclude something about the normalizability. I mean, that was the original question.
Yeah.
No, yeah. Here
It's
you
like
don't.
It's a
Here
construction.
I don't consider normalizability at all. I just consider eigenfunction. It could be non-normalizable. All I know is that it's smooth. Okay. So.
Would discard it if it were not normalizable? Like, for example, isn't a big deal made in that Sethi and Stern paper about the fact that they find normalizable?
Yeah, this is the issue. We would like to understand whether it's normalizable or not, but also we would like to understand the structure.
We won't understand it from a power series.
No, we will not understand it from this perspective. But this is one attack on the problem. Here we consider the structure of the. So you're not only interested in the normalizability, but also, of course, you want to understand the structure of the eigenfunction, because if that could be relevant for the physical applications.
So you still need an existence proof, and then this.
Yeah, exactly. You would need a. Yeah, exactly. You would need a existence, uniqueness, but then this is concerning the structure problem. Okay. Another approach is the deformation, and this was actually also considered by Porati Rosenberg in '98. But here we take a slightly different approach to this and consider. So according to their recipe, essentially what you want to do is you take so here we have these real supercharges, but you can form a complex combination of those, essentially forming a cohomology version of the super algebra. But then you conjugate that by e to some function, so e to some constant times a function, and the e to the minus constant function on the sides of this. So that's the deformation. And this mu here is a deformation parameter. And the idea is to choose a good function here to learn something about the problem, or to maybe, well, what you would like to do is to essentially eliminate the problems, eliminate the valleys or something. But here we consider a certain function which introduces another simplification, or a different type of simplification. So this function is essentially a cubic polynomial, but involving the structure constant SUN. But also you take, well, the gamma matrices, JKL, but then a certain matrix element. So of course this depends on how you choose your representation of this and so on. But choosing in a certain way where you single out essentially so you have this this is again in the 9-dimensional case, I should have said that, but thinking of splitting this into a 7 and a 2-dimensional part, you can, and choosing gamma matrices accordingly, you can make this thing here become the octonionic structure constants, essentially, for this. So in this 7-dimensional case, you have a certain octonionic structure, and depending on how you choose your gamma matrices. And so this becomes a cubic polynomial, and when you introduce this type of deformation, so you form, with this deformed supercharge, you form a Hamiltonian, taking an antisymmetric combination of this, and that is defined as your new deformed Hamiltonian. And this is, again, by the definition, it's non-negative, but depending on your mu, this has a different type of symmetry. So because of the deformation splits essentially the 9 into the 7 and the 2 part, and it preserves certain symmetries in these parts. So in the 7-dimensional case, it's not spin 7, but it actually goes down to G2, preserving the octonionic structure. And in the 2-dimensional part, it's just U1 or SO2. So for mu equals 0, you of course have the original case, but you can see that, well, here I just wrote it out a little bit sketchy, but essentially you see the split in the kinetic energy and the potential in different parts, This HD I will come to in the next approach, but this is essentially involving the two-dimensional part with the 7 coming in as parameters. So it's very easy to study this operator. It's also a supersymmetric operator. And then you have these matrix parts are also split. But the interesting thing is that if you put mu equals 1, you get a truncation of the original operator. And this is what we consider in this paper. So put mu equal 1, you get called H tilde, a truncation. And the property of this truncation, of course, you would like to have something, hopefully with discrete spectrum or something. But what we prove is that it actually also has the same problem of the spectrum, or that this truncated operator also is has a spectrum on 0 to infinity. But the key is that it's simpler now. So it's much simpler to prove this actually than the original one. Because you have this split in different parts. So you can approach it more simply, and that's why it could be useful as a way to attack the full problem if you can prove something for this deformed operator. And this deformation approach, or with other types of potentials and so on, or these deformation functions, has been very successful for simpler models, considered by Erdős, Hassler, and Solovey for the D0, D4 bound state. Okay, and the third approach is this averaging with respect to the spin 9 symmetry. So again, this involves that HD operator that I mentioned earlier, and that coordinate split. So R9 goes into R7 and R2. And so you have the first coordinates here. So you have the full here, and here you have the X1 to X7, and then you have the X8, X9 coordinates. And this operator is then a kinetic energy in the 8-9 coordinates, and it's quadratic in the X8-9, but then you have a certain we call frequency matrix coming in here. So essentially this is just this part is just a bosonic harmonic oscillator with frequencies coming in as the X1 to 7 coordinates. And this part, this is linear in its X and some matrix, but this you can also think of as a fermionic harmonic oscillator with these X coming in as parameters. So this is a very simple Hamiltonian. This is just it's still a supersymmetric Hamiltonian. You can write this as square of supercharges, but it's essentially just a bunch of harmonic oscillators with these X coming in as frequency parameters. So that you can write out the full spectrum of course, depending on the parameters in a complicated way, but still, it's a nice starting point. And the nice thing we found is that you had this operator, and then it's essentially just a truncation or a small part of the original operator. But if you can think of this as sitting somewhere in the space, but then you can actually average this operator. So you have this spin 9 group, which you can act on the operator and essentially rotate this operator in space. And by averaging, you can find a relation between this small simple operator and the full operator. But in order to find a precise relation, you have to rescale the operator a little bit. So, and essentially that just amounts to changing the frequencies, rescaling the frequencies a little bit in this harmonic oscillator. So with this particular coefficients coming in here, so that's the HD prime operator defined in this way, and then if you average this in a precise sense with respect to the spin 9 group, you actually obtain the original Hamiltonian. So the hope would be that since you understand the spectrum of this, if you average the eigenfunctions of this, could you tell something about the full spin 9 symmetric eigenfunctions? This is a tricky issue, but still there's some hope, since you understand everything here. And also it's rather natural that you have to rescale the frequencies a little bit, or you have to, essentially what happens is that you lower the energy a little bit by this change of coefficients a little bit. But what you expect is that if you have a lower energy and then you average that, typically averaging brings up the energy a little bit. So the hope is that if you have it's negative in certain directions, but when you average it, you could bring it up to exactly 0. But of course, this is more of a speculation. But the original operator would not have a chance because it's already 0. Well, of course, you could have. Let's not go into that. Okay, so let's go to the last of these approaches, and that concerns these weighted spaces and a new approach to the index theory. So what we saw from an asymptotic analysis is that you have a polynomial decay of the eigenfunctions in these valleys. So and in the lower dimensions, the decay was not sufficient. So possibly you could have eigenfunctions which, well, they just not decay fast enough, but they still bounded. They behave nicely. So if you allow in the Hilbert space, you allow a slightly less rapid decay, then you can think of these eigenfunctions actually being in the game somehow. You can think of them as being actual eigenfunctions. So that's the idea of this. And also it's motivated a little bit by this d equals 1 observation that you had constant functions. If you want to say you would like to have those also being proper eigenfunctions, then you would allow the constant functions in the Hilbert space. So you have to enlarge the Hilbert space. So this is what we call a weighted Hilbert space. We'll put a W on it. And so that's just the original. So this is the bosonic coordinate space, the Fock space. But then you put in the measure, essentially you put in a certain decay function here. There's a rho alpha, which is defined as, well, it's just some smooth function with a certain decay in x. So this rho alpha, it's just x to the minus alpha as x. It goes to infinity. So if we say had a constant function, then after putting in this rho function here in the integral, of course, the constant function would then have this decay, so it would be in the Hilbert space. It would be integrable. So essentially, you allow the functions to be, they can blow up by more than, or they allowed to blow up by x to the alpha extra when you consider this weighted Hilbert space W. So the inner product in the weighted space is just the original inner product, but with this function rho alpha coming in there. And then there's a mathematical trick to define a Hamiltonian for this in this weighted Hilbert space. So what you want is the Hamiltonian to be, you want the quadratic form of the expectation values of this to be the same as the original expectation values for the original Hamiltonian. But so essentially you want the same operator, but you would want it to have a bigger space somehow. So you can define this by mathematically by Friedrich extension, but you can still relate these two, as I will come to shortly. You can still understand this operator in terms of the other operator. So the idea here is that you have a certain correspondence between ground states. So if you have a proper zero energy state, so it's really a zero eigenfunction of the operator in the Hilbert space. Then by this trick, or by the definition, this will actually also be it will be an zero eigenfunction in the bigger space. Of course, the bigger space contains the smaller Hilbert space. So, but if you have something here, so if you have, say, generalized or weighted zero energy state, then you can actually conclude something, and that's because of these. It involves these supercharges. You can conclude that this is actually also a zero eigenfunction of the supercharge, and it's smooth because of the supercharge was smooth. So if you have something in the kernel of this, so if you have a weighted zero energy state, it is a generalized zero energy state, smooth, but possibly not necessarily rapidly decaying or sufficiently decaying. So finding something here gives you some zero energy state. Okay, so now how can we work with these? The nice thing is that we can relate these two objects. So if you look at in this weighted space and you look at the form expectation value of this form, so HW is the weighted Hamiltonian there, minus lambda. So essentially you look at, you shift the spectrum down by lambda. And then you have a relation, because just how we define these things, this will actually be just the original expectation value of the operator h minus lambda times this decay function, this weight function, rho alpha. So, and then it follows by spectral theory that if you study, so this n here just denotes the number of negative eigenvalues. So if you study, essentially you shift the spectrum down and you look at how many negative eigenvalues you have. And if this is if the spectrum is continuous like this, you get infinitely many. But so by studying how many negative eigenvalues, you can learn what the spectrum is of this weighted operator. So the number of negative eigenvalues of this thing relates to the number of negative eigenvalues of this thing. Essentially a deform. So this is the original operator h, but you deform it with this lambda times this decay function rho. So the problem goes over to studying the number of negative eigenvalues of a deformed or perturbed operator. And that you might be able to say something about. So essentially you can, one way to study this is, so if this weighted operator has a discrete spectrum in the weighted Hilbert space. So if it has to have a discrete spectrum, that means that if you shift it down and you look at the number of negative eigenvalues, that should always be finite. The dimension of this thing should be finite. So if you, regardless of how much you shift the spectrum down and look at the number of negative eigenvalues, if that's always finite, then the operator has a discrete spectrum. So you can conclude that this weighted operator has a discrete spectrum if this thing has finitely many negative eigenvalues. So this perturbation should have finitely many negative eigenvalues. And then you can also say that you can see that there is actually a weighted or generalized eigenstate if this thing has a negative eigenvalue for regardless how small lambda is. So regardless how small you perturb or you shift the spectrum, if there is always a negative eigenvalue there, then of course so essentially you can think of this picture that say that we had a negative or a zero eigenvalue here. If we shift this by an arbitrary amount to the negative real line, then of course it will always be on the negative real line. So there will always be an eigenvalue. So you can determine the existence of generalized zero eigenfunctions by studying this operator. So this is in the original space, and everything is in the original. That's the original operator in the original space with this perturbation. So it's relevant to consider such perturbations. And so at least you can do this for the toy model. You can apply this approach and consider the original toy model supersymmetric operator, perturb it by this thing. And if alpha is sufficiently large, then this has finitely many negative eigenvalues. And you can actually find a bound also on how fast this grows. And if you know these things, then you also know, you know that this weighted operator has a discrete spectrum, and actually you can apply a certain index approach to this. But this also requires knowledge of a related operator, which I will come to. But at least it looks sort of approachable from the toy model perspective. Okay, yeah, this is actually the last slide. So there's just an outlook, and then so essentially the weighted Hamiltonian is you can write in terms of some weighted supercharges, the adjoint Q adjoint times Q. But if you consider a related version of this Q adjoint and a corresponding operator, and you define an index of this, so a trace of this guy, e to the minus beta on that one, minus the trace e to the minus beta on this one, then this actually amounts to a dimension of, so the number of weighted zero NE states minus the number of original zero NE states. And this is independent of beta whenever we have a discrete spectra of these two objects. So this is a well-defined index. Whenever we can prove this is well-defined, and it works for well, if you just consider a free particle on a real line, you can consider a supersymmetric and also the d equals 1 model. For sufficiently high alpha, you can do this. For the toy model, haven't yet proved the discreteness of the spectrum of this thing, but I believe that holds. And then, of course, there's an issue of how you want to evaluate this, and if you can take beta to 0 or whatever possibly makes the life simpler to do this. But at least you have something well-defined. So, of course, we would like to, in the first approach, continue the construction at 0 and at asymptotically. And for the deformed operator, you would like to understand whether there are zero NE states for that one. Of course, you want to average the eigenstates of that truncated operator. This could be difficult, but maybe doable. And in the last approach, we would like to study discreteness of that other operator, consider the index for the toy model as a starting point, and of course, what about extensions to the other dimension or the full matrix models, and whether there is any physical relevance of the weighted zero NE states. That's maybe for the physicists to decide. Okay, thank you very much.
Do we have questions?
The very low dimensional one, the d equals 2 model, has the interesting property that the particles it describes are anyons. So they move in a plane and they have spin a quarter and minus a quarter.
Okay.
So
Yeah, this I didn't know, but
anything you can say about?
But you mean, is this for n equals 2 or for all n?
For all n,
Okay.
if you have higher n, you have n anyons. So if you exchange any 2, the wave function doesn't change by a minus sign as with the fermions, it changes by e to the I pi over 4.
Okay. Yeah, that's interesting. But actually, I've been working on anyons for the last year or so. But I didn't know this connection. Well, I've seen some connections, but not exactly for this. So, but if you consider the quantum mechanics of anyons, just non-relativistic quantum mechanics of anyons, you can prove. You can prove certain things with that. Or you can essentially. We have a lower bound for the anyon gas, for instance. And,
so these are supersymmetric anyons.
Yeah, okay, yeah. So in the case of supersymmetric anyons, I don't know much. This is just, I only studied the simplest case of spinless non-relativistic anyons and so on. But,
Julian and I thought we discovered this, and we wrote a paper, but then it turns out it's in a footnote of a paper by Witten from 10 years earlier.
Okay.
You didn't need to say that one.
But it sounds interesting. I would like to hear more about that.
Any more questions? Okay, then let's thank Douglas again.